Hello?
Hello.
Hi.
Hi.
How's it going?
Good. How are you?
Doing good. Doing good. Yeah, sorry, I couldn't hear you for a sec, so I just wrote this on the screen there.
Yeah.
Have you ever used the platform before?
Yes, a couple of times.
Okay, so then I guess you're familiar with how it all works, and so then I'm just going to jump straight into a coding question.
All right.
So the first question is, are you familiar with the concept of order statistics? Have you heard that term before?
No.
Okay. It's a very simple thing with a overly complicated name. So given a unordered set of numbers, like what I've written here, the order statistics are like the nth element in the list if it were sorted. So like the first smallest number in this list is going to be 1, and then the second smallest number is 2, and then basically the order, in terms of the order, the nth order statistic is then the nth smallest. Does that make sense?
Yeah.
I guess this is a bad set of numbers to have chosen. So then this makes it a little more clear.
Mm-hmm.
All right, so we're just going to have some algorithmic questions about finding some of these nth order statistics. And just to get started with sort of a warm-up problem, how about if you write a function that, given a list of numbers that are out of order, you just find the smallest. So basically the first order statistic.
Okay. Sounds good. So I'll just declare it here. Public static int is the return. And then I'll just call it min.
Yep.
And this takes int, I'll call it n. All right. So then here I'll
So then take in yeah, this will be like an array. Yeah. Yep.
Yeah, sorry. Okay. You know what? Oh, okay. So then I'll loop through the array.
Mm-hmm.
And then for each of those iterations, I'll compare it against a min that I've already set up. So I'll set the min to be ARR at 0. And so what should I return if the array is null, or if there's no values?
Don't worry about that case. We'll just assume it always has some values in it.
Okay, sounds good. So then we'll set the min to the first one, and then going through if the so then we can actually start. Okay, yeah. So then going through to looping through the array, if the if the element at the index of I is less than min, then we make that the new min. And then at the very end of the for loop, we return min. Yep, so just to test it to make sure, I'll write a little test here.
Sounds good.
So input is equal to, let's see, so like 2, 3, 0, 6 should give us 0.
Yep, sounds good.
Min input, and let's try that then. I put it inside the for loop. Okay. All right, there we go. So it returns 0.
Perfect. And what's the runtime of this algorithm?
Oh, then.
And is there any faster way that you can do it?
For an unsorted array that I know of, no.
Correct. Okay. So now you definitely got the idea. Now let's make this a little harder, a little trickier. And how about you give me the second smallest number?
Okay. So for the second smallest number, then I think what we would need to do is maintain two variables and then kind of check across both of them to see like sort of like a larger min and a smaller min or something like that. So then we can check to see if there's a number that's smaller. If it's smaller than both of them, then we'll put it into the smaller min. And if it's only smaller than the larger one, then we can put it into the larger min, the new larger min. So once again, are we assuming that the array's length is 2 or greater?
Yep.
Okay. So then I'll just call this min2, and we'll put this at the second element of the array. And then here, if the array is greater than the min, then it's the very smallest one. So the min becomes array at 1, and then min2 becomes min, well, we'll do this first. So then min2 should be set to min, and then min is set to the new minimum. And then otherwise, if the array element is less than min2, sorry. Okay. So if it's less than min2, whereas it's still greater than min1, then this means that this should be set to, so then min2 becomes the new element, and then instead min becomes min2.
Min2 becomes the array. Wait, but what happened to min then?
Oh, sorry, yeah, this is maintain the same, I think. Yeah, because if it's less than min2, then min1 is still the smallest, so then that should stay the same, but min2 gets updated.
Okay. Yeah, let's run this.
Oh, I have to return min2 this time. Okay, so this one should give me 3. Oh, sorry, it should give me 2. Okay, there, give me 2.
Yep, perfect. Okay. Yeah, interesting. I'm trying to think if there is, I'm trying to see if there's a corner case here with the fact, does min2, what if, yeah, I guess, what if these were the numbers here? I'm trying to think. Let's try those out. So so it should actually be 3, because 3 is the second smallest.
Yeah, sometimes 3.
And so min2 gets set to, I guess I'm just looking at this. Oh, what if
there were 2?
Because you start back at 0 again, and then you flip it all around. I got it. Okay. Yeah. Perfect. Okay. And what's the runtime of this one?
This one is still open.
Okay. So let's just say that we're, as you might have guessed, we're going to want to move this and turn it into n. So we're going to want to add another parameter here that says I want to find the nth smallest. Now, one way you could do it is you could just expand on this idea, and you could just create sort of a list of all of the mins up to up to n.
Right.
Now, what would the runtime of that algorithm be?
Well, if we're storing them all, then we need to check across each of them each time. So the runtime would become n squared since we're running through all of the previous values every time we go through the array.
Yep. Okay. So to get the 0th or the first, it just took O of 1 or O of n. To get 2, it took O of n. But now if you expand this in that same sort of pattern, it actually becomes O of n squared. So
Right.
Is there a way that you can improve on that O of n squared time?
All right, let's see. So maybe there's a way where actually, yeah, I think one way to improve would just be to sort the array, and then that would make it n log n immediately. And then all we'd have to do is find the nth index in the sorted array.
Yep. Okay, perfect. Now, here's the real challenge. Can we do better than n log n for any arbitrary? Actually, I guess I gave this the wrong letter. For any arbitrary m that we're trying to find. So we saw that when m is 1, we can do it in n time. When m is 2, we can still do it in n time. Do you think that there's a way that you could extrapolate on that sort of pattern and say, oh, I can just always do it in n time, no matter which one of these I'm trying to find?
Right. So the reason why we could do it in O of n time for if n equals 1 is because we could just go through and compare them all and see whichever one is the smallest. And then for n equals 2, we had to compare it with each of them and also the previous minimum. So, without having to compare it to all of the previous minimums, I'm trying to think if there's a way to figure out the nth smallest. Maybe if we delete certain objects, but then that wouldn't help either because if we go through.
But if you delete.
Yeah, but that wouldn't work.
So it's tricky. So if you get stuck, I have some hints for you.
Yes, I would appreciate a hint.
Okay, so so you mentioned the n log n case of sorting and then just picking the mth item in the list. So in that sense, once we sort this input, when you have 2, 3, 5, 6, and then let's say your m is 3, and basically you just go straight to the 5, right? And you know that 5 is in the correct place, and that it is that everything to the left is below it and everything to the right is above it, and it's in position number 3. So that means it's necessarily correct. Now, what you've also done, and actually, if we expand this out just a little bit more, then I guess I can just do this. then what you can see is 10 and 15 and 21. So you had that this number 5 is in the correct position, but also every single other number is also in the correct position. So you've also done work to make sure that the 3 is in the second position, and the 2 is in the first position, and the 10 is in the fifth position, and you've put them all in the right places, even though at the end of the day, all you really cared about was that that 5 was in the right place. Because whatever order any of these other ones are in, it doesn't really matter. You don't really care because you're only interested in this one.
Right. Okay. That's interesting. So basically we're looking for a way to ensure that a certain value is in a certain spot, but all the other values don't have to be sorted.
Correct.
Okay. And the one that we want to be in the right place is at the M index.
Right.
So if we did this for the first minimum, then basically we would have to go through each of the elements and then put all of the ones that are larger than a certain minimum to the right of it so that it would be at the beginning. So basically we would have to go through and figure out like how many numbers are lower than that number and how many numbers are larger than that number. So what if we try to do that then? Is it like maybe there's some way that we can balance? So say we want M to be 2, like in this case where the index is 2, that means that we want 2 numbers to be less than the one at M and then 4 numbers to be to the right. So then maybe we can sort of like choose somehow there should be a way where we can go through and figure out and make it balanced so that it's like equal on both sides, even though those aren't sorted. But we would need to know what the number 5 already is in order to go through and actually put that in its right spot. So there needs to be a way where we can figure that out without knowing 5.
Right.
Yeah, and if we just chose a random number or went one by one like we did here, then it wouldn't work because then we would still go back to being n squared. We just still have to go through all the numbers to see which one was right.
Right.
Huh.
But let's take a look at that example that you had just said that you just talked about saying you kind of described this process where you take this input array, you take the first number that you found, and you made sure that it went in the right spot, right? So you described a process of saying take this number 3 and put it just that one number where it goes, so that everything to the left is less than it and everything to the right is greater than it.
Binary search tree.
What was that?
A binary search tree?
Yeah, I mean, so there's that's kind of a part of it. But so describe how you might do that. How would you find, so just given, I mean, you don't really have much information about this this array coming into it because it's unsorted. It could be in any order. So you might as well just start with the first number you find and say, I'm just going to put that first one where it belongs, and then I'll tackle the rest of the problem after that. So, for example, you can think of what it would look like afterwards would be 21 and 15. So you can imagine that this might be what the array would look like after you found the first place. So 3 goes in this spot, and everything to the left is less than 3, and everything to the right is greater than 3. And you still don't really know about what's going on either side, and you haven't really sorted it altogether, but you do know that 3 is in the right spot.
Mm-hmm.
So does this then give you some additional information in terms of now trying to, like, where would you proceed from here? So keep in mind that, like, we're still looking for the third largest number, and you just figured out that the number 3 goes in position number 1.
So then I know that the number 3 is the second largest number, and at this point I would have enough information to find the third largest number using the technique that I just did before, where if I know the previous minimum, then I just have to run through the array one more time to find the next minimum.
Right. That's true. But in the and which part of that array would you run that algorithm on? The whole thing or a part of it?
The right, because the right is the part that's unsorted.
Right. Well, actually, in a sense, the left is also unsorted, kind of, because you don't really have any guarantees about what's going on to the left. I mean, in this case you do, because there's only one element, so there's not really much sorting to do. But but what else is an interesting property? So now that you have this 3 that's in the right spot, what do you know about, like, in terms of what you're looking for? Are you interested in anything on the left, or are you interested on anything on the right, or are you interested in both sides?
Well, right now, looking at this array, I would be interested in the right, since the 3 is only an element at index 1, but what we're looking for is index 3.
Mm-hmm.
But in terms of ordering, what we're looking for, and since, but the 2 could be the 5 too. Like, what if there was a 5 here instead of the 2? But then, yeah.
It couldn't
so then
be.
If,
it couldn't
then
be, because you've split this this array up. Maybe I wasn't clear in exactly the thing that I did, but if let me start by just kind of like rearranging this a little bit more and making it kind of a little more random, and then sort of I'll do it again. So given, and I guess you've been talking about sort of yeah, well, okay, we can just keep this the way it is. But so you start with this 10, and you first make sure that everything on your left is less than 10, and everything on your right is greater than 10. So this might look like this: 2, 5, 6, 3, 10, 15, 11. So you've just you've shifted things around, but you've shifted them around in a way so that everything on the left is less than 10 and everything on the right is greater than 10. So it's not just that you found that the one right place for it, but you've done a little bit extra to make sure that you've split the array in 2 pieces.
Yeah. So then this is actually pretty helpful, because if the 10 is over here, and this is in the 1, 0, 1, 2, 3, 4th index, then we know that M has to be to the left of it. So we don't really need to worry to the right anymore, because those are greater than 10 anyway.
Exactly. So then when you repeat this and you sort of go for another iteration of it, you're only going to be looking at the left side, right?
Yeah.
Yeah. Okay. So does that give you some ideas about how this algorithm might work?
Yeah, it does. Yeah, because then in the first time around, I'm iterating through all the numbers to find where it belongs. And then the second time around, I'm only iterating through the left side. So this kind of reminds me a little bit of like binary search. So maybe the runtime will also get a little bit better than n squared when we do it this way.
Okay.
All right, so should I start implementing it then?
Yeah, let's see what happens.
All right. So we're outputting just the number this time again. Okay.
Yeah.
And this is the nth smallest. Okay, so first what we have to do is, well, I'm just going to write the code for the first time, and then we can probably iterate through and make that repeat. So the first time around, I'll have to go through the entire array. And then, so I'll have to select. So if I look at the first one, I'll have to put it in the right spot. So then I'll take sort of like index to be placed. I'll just call it index. Is, let's say, I.
Mm-hmm.
Or actually, yeah. If we make it 0, actually before the array, before this loop, then we're looking for. So this looks at. We're going through them, and then if we say that if the item at that index is less than, or if it's greater than whatever is there, then we need to move it to the right. So kind of like swap it. Yeah, so if the array at index is greater than array at I, then we need to do some swapping here. So just to make things, should I just kind of abbreviate it and just write swap here, or do you want me to write the whole swap?
You can just write swap, that's fine.
Okay. And then, well, actually, I'm going to need to test it later, so I might as well just do it now. Never mind.
Right.
So then we'll write in temp as array at I, and the array at I is equal to array at index, and array at index is equal to temp. So this switches them around if it's greater than, but if it's less than, then essentially we need to, well, we just need to keep moving actually, so we don't need to do anything there. But if they're equal to each other, then we stop. Yeah, so if the array at index is greater than, wait, did I do this right? Let's see. So we start with index equals 0. And if it's greater than, oh, okay, there's a problem here, because if it's starting with the first one, then it'll just stop immediately since it's equal to the same one. So then we'll start at the first here.
Mm-hmm.
Yeah. So then if, okay. So if we start with the first one, then first, so index is equal to 0. And the first element is 10. And then it checks to see at array at 1, which is 2, and 10 is greater than 2, so then it swaps, and now it's 2 and then 10, and then it compares it against 5. 10 is greater than 5, so it swaps. 6 is greater than 5, so it swaps, and then it looks at 11, and they are, okay, so this breaks now because it'll stop since it's greater than, but it needs to continue and look for that 3.
Wait, it wouldn't break. So those two numbers don't equal each. So that's.
Wait.
Yeah. So,
yeah,
so
you're right.
10 doesn't equal 11.
Yeah. yeah, so it wouldn't stop, but it still needs to, well, yeah, so, okay, never mind. Yeah, it would stay there, and then it would go through and then check against 3. And then now that it's less than 3, it'll swap with that one instead. And then 10 will be where the 3 was, and then it'll check against 15. It's greater than, so it'll stay there. And that puts it, wait, then that's not right. Oh, wait.
So that would actually work for this specific input, but think about what would happen if the input was something like this. So, you first swap the 10 with the 2, so that's right, and then you swap the 10 with the 5, which is totally right, and then you swap the 10 with the 6, then you leave that, then you swap the 3 with the 10, so that's cool, and then you swap the 0 with the 10.
Yeah, that's not right.
That's not quite right, because when you skipped over the 11, now you have something on the left that is bigger than it should be.
Mm-hmm. So then I think maybe we have to move the 11 along with the 10 now every time. So maybe we can swap the 11 with whatever's next to it so that it keeps like sort of moving away.
So swap the 11. So you had this point where you had the 10 and the 0 is like this.
Mm-hmm.
But then what were you going to do?
No, if
Then
one
you swap the 0 and the 11?
No, if yeah. No, if like the 10 was here.
Mm-hmm.
What was here before?
It was a 3, yeah. Mm-hmm.
Yeah, and then you would check the 10 and the 11, and then since 11 is greater, you could swap it away so that it goes to, yeah, you could actually just swap it with like the end of the array. So then this becomes 0 and this becomes 11.
Mm-hmm.
And then here we check against the 0, it's greater than, and then it swaps. And then you check the 10 and the 3, it's greater, so it swaps.
Okay.
And then that one's in the right place.
So then presumably if there was another number that was greater than 10, you would swap it. So like, so we had it here that was like 10, 11. So we're sort of looking at the 10 now. The 3, and we had a 15.
Mm-hmm. So then it would first compare the 10 and the 11, and then it would swap. Oh, okay, now I see what you're saying. Then once, if it swaps there, it'll just skip over and it wouldn't work, so.
So, but you're definitely on the right track. Like this is definitely the kind of sort of manipulating that you're going to want to be doing in this array. So, and definitely you're definitely on the right track with respect to looking at, when you started with this number 10, and you're looking at each one of these numbers as you're going up, and as long as it's less than, then you're sort of keeping it to the left, and as long as it's greater than, you're keeping it to the right. So that's kind of how you're sort of scanning this list of numbers. So can you think of a way, and yet, so you hit into this one sort of problematic case that when you start to have multiple numbers that are bigger, then it gets kind of tough with how do you deal with the sort of bookkeeping of where does it go? Who can you swap it with?
Yeah.
So
well,
can you
I can think of one. Yeah, I can think of one way to solve that, which would be to just create another array And then if it's less than the number we want, we put it into the beginning of the array and hold two sort of like counters for where the beginning of the array is and then where the end of the array is. And then if the number is larger, we add it to the end until there's only one spot left, and then that's where the 10 has to go.
That's a good way to do it.
All right, so then I'll try to implement that instead. I'll just erase this. Okay, so then we have now two counters. So int start is equal to 0, and int end is equal to the array.length. And then we loop through. And so we know the number that we're looking for, so I'll just, I'll put that in as, I'll just put that in as index again, and then that'll start at 0 this time. And then, so basically, if the number that we're looking at right now, which is array at I, is less than the array at index, then we put it to the right. So then we have this new array that I have to create. And it's the same length. And then if the array at I is less than the array at index, then it should go in the beginning. So then it does int at start. Oh, sorry. What did I call it? New array. New array at start becomes array at index. And then we have to do start plus plus to show that we've added an element. And then if the...
Is it an array at index or array at I?
Wait, sorry?
Is it so in this line here, you said new array at start is array at index. Is it index or is it I?
Oh, sorry. Yeah. I should have used a different name. Yeah. Okay. And then are there going to be duplicates in this array or no?
Let's just say no for now.
Okay, so if there's no duplicates, then any other element we look at cannot be the one that we're searching for. So then we can just do an else here. And then this basically says that the array at I is now greater than what we're looking for, so it needs to go to the right. So then it goes to new array at end is equal to the array at index. Yeah. Wait. No, I. I made the same mistake. Okay. And then do n minus minus. And then this loop has to end whenever start and end are one apart from each other, because then that means that we have found our index. Then I'll just do an if here. So if start minus or end minus start is equal to 1, then we return start plus 1. All right, so I think this should work for the first one to place it in the right spot. So let's try it.
Oh, I see. So this is going to be sort of so I see you're like returning the number right away, but I'm wondering, so this is going to return not the nth smallest, but this is going to return some smallest that you're basically going to return, the index. You're returning which position the first element will have gone to.
Yeah. I just wanted to break down the problem, so I wanted to see it.
Got it. Okay.
Okay. So in this specific array, I'm not actually sure where this 10 is supposed to go. 1, 2.
So 2, 3, 5, 6. So it's going to be 4.
Okay. Should be 4. input, and M, we don't really even need M.
Yeah, it's not. You don't even use M, so.
Oh, I need to mention something. It's not there.
So here's an interesting question. So when will end minus start equal 1?
And what?
So this line here, number 42. When will this be true?
End minus start will be 1 when we've gone through all the elements of the array, and now we're looking at that one empty space where the element should go.
Okay. So if that's going to happen once you're already completed with this array, is this ever going to be seen?
Oh, yeah, you're right. It will just be right after the for loop, so we can just return after the loop, and then we can return start before.
Yeah. Index out of bounds.
Okay. It has to be laid up one through.
5.
Okay, so it's just 5.
So 0, 1, 2, 3, 4. I think actually, because you incremented start right here, you don't need to increment start there. I think that's what's going on.
That makes sense. All right, and let me try it with another, just to make sure. So now if we deleted one of these, then it should become 3, I believe.
Yep.
Yeah. Okay.
All right.
So now I have the functionality for figuring out the spot where one specific element should go. But I have to repeat this until I find wherever the element at the mth index is. So essentially, this whole start, if start is m, then we know that we found our element.
Correct.
But the thing is, this index has to change every time. So I'm thinking maybe we can sort of do this like a binary search where we choose like the middle number in each half, and then we try to put that where it belongs. And then if m is greater than the index there, then we run it on the right half, and if m is less than, then we can run it on the left half.
Sounds good.
Okay, so then here we'll start with, instead of 0, we'll do start plus end divided by 2. Here, okay. And then so then looking at the end.
So the index is representative of the of the index of the number you're comparing everything with, right?
Yeah.
So in that sense, index represented this number 10 here. Yeah. Does it get you anything to pick the number in the middle? Like this number here is the number in the middle. Does that one really? I mean, does it really matter whether? I mean, remember this is an unsorted array. Does it really matter that you take index 0 or you take index start plus end over 2?
No, it really doesn't.
It's not going to really be that it's going to be 50-50, right? It's not going to be exactly in the middle there. And there's kind of no way to tell where, like, how well this number that you're picking at random is going to split this array in two. So, I mean, you can do that, but I think starting with index 0 is a totally reasonable way to go, because at this point, it's just a random array. There's no order, so you might as well just pick anything, and then go from there.
Yeah, I think that's fine. We can use 0 then. Yeah, and then I think we can actually make this recursive to maybe do a little less work, where once we find where the spot that index should go, then we'll determine whether m is on the right or left, and then we can go again and do it. But actually, that might be more. Yeah, I think that might be one way of implementing it, because then we can always keep index as 0, because then the array that we're looking at is now like a subarray, so the index will always be 0. Or when we could do this, just have index at start and then loop through and then kind of just keep doing it with a new start and end. That would be another way of doing it. So yeah, or we could just like make new parameters here for start and end and then implement it as recursive. So there's like multiple ways that this could go.
So I like your recursive idea because it's definitely going to make the code a little bit simpler. Do you actually need to add more parameters here if you do it as a recursive algorithm?
No, I don't have to. If I change the array, then I don't have to. Yeah, I'm just wondering, like, that would still take up more memory, because technically, like, I would have to somehow cut off the array. But I feel like that's going too far into it. So we'll just keep it like this, and then I'll try to turn it into a subarray. Okay, so then, where are we? Okay, so we're using index 0, and then at the end of this, we're returning start, which ends up being the index of whatever element is at 0. So then here what we need to do is determine if m is greater than or less than start. So if m is greater than start, then we know that we need to redo this on the right side of the array. So then we should form n smallest on, I actually forgot the method for subarrays in Java.
I think, yeah, I'm just looking on the, I think there's a thing called range, no, subset, fill, substitute, subsequent, copy of range. I mean, you could just use copy of range if you wanted to. It's not that bad.
Okay.
So it looks
I think
like,
I got it. Yeah, there's like a code completion on here, and it says that it's a method, so I'll just use that then. So copy of, okay. Yeah, so then the original would be ARR, and then from, I'm assuming that the from is inclusive, so then we would use start plus 1, because start we've already looked at, and that's the one that we found. And then the end would just still be end. And then we can delete that. And then here would be the other way around. So if we have n smallest, then it would be array, and then instead of start plus 1, this would be 0, and this would be just start. And then else, that means that m is equal to start, which means that we found the element at the index that we want, so we just return start.
Okay, nice. Now, n smallest actually takes 2 parameters.
Oh, right. So then m, I just need to add in.
Is it m? Because that's relative to the entire,
Right. It would, so for this, right. So if the m that we're looking for is greater than start, then it would need to be m minus start. And then if the element that we're looking for is, oh wait, I messed this up. So if m is less than start, then now we're looking for still m. Yeah. Okay. Right. So now it looks like, all right. I'm going to test this now to see if there's any issues.
Okay.
Let's just see if we give 0 as m, then we should still get back 10. So let's just see if that's...
we should get 3. So 3 is the smallest. 3 is the smallest one.
Oh yeah. So then it should give back 3. Okay. Looks like it has.
We need to import. Wait, is arrays? Java util. Oh, that's Java util. It's a lowercase c.
Oh, okay. All right, let's see what happens now. Oh, I'm missing a return statement.
Because you don't have return in these ones.
Wait, which one are they looking at?
So 52 and 54. You're calculating it without returning it.
Got it. All right. Now it's giving me 0, which that wasn't even in the input array.
So
this is the index, so I have to return at start.
Right.
Oh, that's still not right. All right. Let's see.
So definitely the logic looks right. I'm guessing there must be some kind of off by 1 bug. So we already figured out that with this list, when you go the first time, start equals. Oh yeah, wait. Start was 3 before, so it should have put it in the. So maybe there's some need to do some debugging with some print statements to see, because yeah, definitely the logic here is looking solid.
Maybe here I'll just print out a new array. Okay. So the new array, the first time. Oh, I think it's because. No, that's not it. Okay. So 5, 6, 3, 15, 11, 10.
Interesting that you have the 10 in there. So in that sense, I think you want your new array to be 1 element smaller. So if you see what's happening here is that you started with index 0, and then you're also checking index 0 again. And really, your the size is going to be 1 less, because you're kind of taking 1 out,
right,
and then sort of partitioning it after you've taken that 1 out. So then now there might be. So now that you've like reduced the size by a little bit, now you have to make up for that when you make this copy.
Well, that wouldn't be affected by the new array, would it? Because the new array.
If you look at. Well, see, so now the end actually has to be array of length minus 2. So right, you have to start because the end is actually the end of new array dot length minus 1. If that makes sense.
Oh, right. Well, it's the initial array minus 1, so it's like the ending. But then in the new array, it's not.
So in the new array, so
Oh, it's
so
not actually.
I mean, you're placing these you're placing you're copying these values over into the new
I
array. So
yeah.
the
So
new array has to.
yeah. All I
Wait.
had to do was replace array.length here because the end is not actually the end. It just starts with 2. But what I'm looking
But
at here.
I'm looking at 38 here.
Oh, yeah.
So that end is actually the end of new array dot length minus 1, which is the original array of length minus 2.
Oh, okay.
And then in this one, you're not actually copying the original array. You want to copy the new array because the original array is like totally out of order.
Right.
And the new array is the one that, yeah. And also you'll need the new array dot length.
Oh, okay. I get it. And new array has to be smaller.
Yeah.
Wait, why did? Yeah, it should be 1 smaller, right? Because it's not including the 10 itself, like the number it's looking for.
Right. So in this one, you want to just copy to new array dot length.
Well, new array.length would include the values above it, wouldn't it?
Well, new array dot length is the end. It's the end of the new array, and you're trying to copy like from your position all the way to the end.
Oh yeah. Okay. So then here, there's still something wrong with the size of new array.
Wait, you can try writing again. What's wrong with the size of new array? 46. New array. And, oh no, this one here. Wait, you had just changed it. 38.
Oh.
You had just changed. Yeah.
So this should be at -2.
Yeah. Or you could also just set end underneath the new array, or you could move this one up and just say end is new array dot length minus 1. Either way, it's the same number.
Oh, okay. And then this shouldn't be, yeah, okay, and this is still ARR.length minus 1 since this one's smaller. Okay, now 3. Okay, yeah, that's actually right.
There it is. Not bad.
There we go. And let's try it for some other numbers too. So if we tried like 1, then that should give us 5. And it gives us no.
Close.
Okay.
All right. Yeah, I think there must be. I'm guessing there's like an off by 1. My guess is there's off by 1 in either in this m minus start or this m here or the 0 to start or there's. I'm guessing there's like a tiny little off by 1 bug in there somewhere, which is not a big deal. Just because we're running a little bit short on time. So you definitely you did all this work, and now you are you're inspecting less and smaller pieces of the array as you recurse into it. What is the runtime of this algorithm
now? Okay.
So the question is that so you did all this work, or there's all this extra code to like be careful not to do any more work than you need to. So the question is, has this actually sped it up, or is it still n log n, or is it even greater than n log n?
Well, I think it depends on the case, because say for example, if this array was like sorted in backwards order, maybe, then basically the first one that we would look at would be placed at the end. And then we go back into the left side, and then the first one would be placed at the end again. And then say our m was 0, then we'd have to keep going through that array over and over. And so we'd basically be looking at the entire array, so like 1, 2, 3, 4, 5, 6. So that'd be 6 plus 5 plus 4 plus 3 plus 2 plus 1, which in the end still comes out to O of n squared. So I think in the worst case, our new algorithm is still O of n squared.
Okay. But what about in, say, the average case? Like, what if, for example, you randomized, like that's sort of a common thing that people do with these kinds of divide and conquer algorithms, is that if there is kind of a like a poisonous input, then you just kind of randomize it to make sure that it's that there's no that it's just going to be kind of in this big old jumbled order. So what can we expect sort of on the average case? You're totally right. There is there's a worst case input that makes it n squared. But what can we generally expect this to be in the average case?
I think this is still n log n then, because we're looking at the first time. Well, the first time, so in the average case, it would be like we're looking at half the array, since then it wouldn't be too much and it would be too little. So the first time we would do this, and then, we're looking at half. So then, actually, we would look at 6 and then 3 and then 1, which is like n log n, I would say.
Close. So can you see me typing among the n smallest? So so the first time you run through this, in the first iteration, you have n elements that you're going over. And then, like you said, you break it down by half, and then the next time you just go over the n over 2, right? And then the next one is n over 4 and n over 8, etc. So what is that going to add up to?
Log n.
Is it?
No, it's just n.
Right. Exactly.
Yeah, it's 2n, which becomes n. Oh, okay.
Yep. So you did it. You got it down from n log n to n. And the trick is that when you do the sort, you have this halving that you do each time, but you keep doing more and more work. So times n over 4 plus 8 times n over 8.
Was increased in the sorting.
Yeah. So when you do a sort, you split it in half, and then you do both sides. And so even though it's getting smaller and smaller, you have more and more of them that you have to kind of deal with. And so the length of this is log n. So like the number of iterations is log n. And so then that's why it becomes n log n. But in your case, you don't have this ever increasing coefficient on in front of it, and so it just adds up to 2n, and it's bounded. So you got it. Very good.
All right. Thank you. This is a really interesting problem.
Yeah, I'm glad you liked it. So I'll leave some comments and stuff on the platform, but just before we go, if you have any questions for me about interviewing or anything else, I'd be happy to answer them.
I think I'm all set. The feedback when it comes through.
Okay, awesome. Then you have a good night and good luck with all of your future practice rounds.
Thank you.
All right. Okay, bye-bye.